Welcome to the deep dive. Today, we're really digging into one of the biggest physics stories of our time, LIGO. We're looking at the history, the incredible tech involved, and just how scientists managed to measure space-time actually wiggling.
It sounds like science fiction, doesn't it? Measuring the fabric of the universe.
It really does. Okay, so let's set the stage. We have to go back to Einstein, 1915. General relativity. The idea wasn't gravity as a force pulling things, but mass actually warping space and time around it.
Right. The classic image is like a bowling ball on a trampoline distorting the surface. That's sort of what the sun does to space-time, and planets follow the curves.
Exactly. And then just a year later, 1916, the math pointed to something else, gravitational waves.
If something really violent happens, like, say, two black holes smashing into each other, that disturbance in space-time should ripple outwards.
Like dropping a stone in a pond?
Kind of, yeah. But these waves are they stretch space in one direction while squashing it in the perpendicular direction, all moving at light speed.
So the theory was there pretty early on, but Einstein himself was, well, pretty skeptical they'd ever be detected, wasn't he? He thought they were just too weak.
He did, initially, and he had good reason. I mean, the universe is just incredibly stiff. Space doesn't like to be distorted.
Stiff? How stiff are we talking?
Well, we measure the effect, the strain, as h. It's the change in distance divided by the total separation. And the numbers are just vanishingly small for almost anything. Like, imagine two trains colliding, a huge event on human scales, right? The gravitational wave strain from that would be something like 1042.
10 to the minus 42, that's nothing. Basically zero.
Pretty much. To put it another way, at the frequencies LIGO listens to, or in 100 hertz, space is about 10 times stiffer than steel.
100 billion times stiffer than steel.
Yeah.
Okay, yeah, I see why he was skeptical.
Yeah.
So direct detection seemed impossible for a long, long time.
Right. But crucially, we got really compelling indirect evidence first.
Hulse-Taylor, a binary pulsar.
Exactly. Back in 1974, they found this amazing system, two neutron stars orbiting each other. And they could measure their orbit incredibly precisely. What they saw was the orbit shrinking, the stars spiraling inwards, losing energy exactly at the rate general relativity predicted they should be losing it, through emitting gravitational waves. That won them the Nobel in '93.
And the effect wasn't subtle in cosmic terms, was it? You remember the comparison. Mercury's orbit precesses shifts by 43 arcseconds per century. But this Hulse-Taylor system, its closest approach point, the periastron, was shifting by almost 4 degrees every single year.
It was GR in action, writ large, a perfect confirmation that gravitational waves were real and carried energy away, just as Einstein's theory said.
Okay, so that set the stage. We knew they were out there. Now came the frankly insane challenge, actually catching one directly.
The target for LIGO was a strain sensitivity, that H value of $1021 or better, tiny.
And with their detectors having 4-kilometer-long arms, what kind of distance change does that translate to?
It meant they had to be able to measure a change in the arm length of about 1018 meters.
10 to the minus 18 meters. Wait,
yeah.
Isn't a proton something like 10-15 meters across?
Yep. So they needed to measure a distance change about 1,000th the width of a single proton.
How is that even possible? You mentioned earlier just regular ground vibrations are way, way bigger than that.
Oh, vastly bigger. Typical seismic noise, even at quiet sites, is around 10.6 meters.
So they needed to somehow ignore or cancel out noise that was 1 trillion times, 12 stronger than the signal they were looking for.
Basically, yes. That's the monumental engineering challenge LIGO overcame. The core design, heavily influenced by Rainer Weiss's early work, uses a Michelson interferometer, big L shape.
Right, the idea being a gravitational wave would stretch one arm while squeezing the other.
Exactly. The wave's passage changes the relative path lengths for laser light going down the arms, and you measure that tiny difference when the beams recombine. But getting the needed sensitivity, that took layers of innovation.
They couldn't physically build arms thousands of kilometers long, so they had to make the light travel further within the 4-kilometer arms.
Precisely. They used Fabry-Perot cavities, basically mirrors at each end, to bounce the laser light back and forth hundreds, maybe thousands of times, effectively making the arms much, much longer optically.
Okay, so that boosts signal. What else?
More laser power helps. They used techniques like power recycling to effectively trap light in the system and build up its intensity, acting like a much stronger laser source.
Right. But still, that seismic noise, 1 trillion times stronger.
That was arguably the hardest part. Dealing with noise, seismic noise shaking the ground. Thermal noise jostling the atoms in the mirrors themselves.
How do they tackle that?
With incredible isolation systems. The main mirrors, the 40-kilogram test masses, hang from quadruple pendulum systems. Think of swings hanging from swings hanging from swings.
4 stages of damping.
Yes, and they hang from incredibly thin fused silica fibers, basically glass threads, to minimize thermal noise transfer. It's an amazing piece of mechanical engineering designed to let the mirrors float as freely as possible, disturbed only by gravity itself.
And building 2 detectors, thousands of miles apart in Washington and Louisiana, to make sure any signal seen wasn't just local noise.
Absolutely crucial for confirming a real detection. Seeing the same chirp arrive at both sites slightly offset because of the light travel time difference.
So this whole journey, only 45 years from concept to first detection, supported by the NSF, even when a lot of people were skeptical.
It really was a marathon. It took immense perseverance and belief, transforming a wild idea into a whole new field. Gravitational wave astronomy, we've opened a new window on the universe.
It's an incredible achievement. And it makes you wonder, you mentioned that initial proposal pointing out the 10-60-meter ground noise versus the 10-18-meter target.
Yeah, that factor of a trillion.
If they managed to bridge that gap, to hear that whisper from the cosmos over the roar of the Earth, what other things do we think are impossible measurements right now that maybe future scientists will figure out how to crack?
That's the exciting question, isn't it? What fundamental limits are just waiting for the next ingenious solution?